Sample problem 6.6. An electron in a hydrogen atom is known to have a velocity of 5 times 10 to the 6 meters per second plus or minus 1%. Using the uncertainty principle, calculate the minimum uncertainty in the position of the electron. And given that the diameter of the hydrogen atom is less than 1 angstrom, comment on the magnitude of this uncertainty compared to the size of the atom. This is a Heisenberg uncertainty principle problem. And so let's remind ourselves the equation for this is that the uncertainty in the position, delta x, times the mass of the particle we're concerned with, times the uncertainty in the speed or velocity of the particle has got to be greater than or equal to h over 4 pi. So in this particular problem, really what they're trying to get us to figure out is the minimum, meaning it could be more, it's greater than or equal to, but it's at least equal to h over 4 pi, and on the right side of the equation. What is the minimum, the smallest value delta x could be? That's the position, that's the uncertainty in the position. Okay? So if we're trying to find delta x, we just got to move m and delta u to both sides. So how do we do that algebraically? We divide both sides by m delta u, right? So on the left side, the mass over mass is 1. Delta u over delta u is 1. And now we have the uncertainty in the position is greater than or equal to h. Let's move these up here, right? They're in the denominator. We're dividing by them. So h over 4 pi m delta u. Okay? Now let's be careful. The velocity of the electron is 5 times 10 to the 6 meters per second. But we don't need the velocity in this calculation. We need the uncertainty, delta u. And it says the uncertainty is plus or minus 1%. So that would be 1 out of 100, 1%, 1 per 100 times the velocity. So that would be 1 over 100 times 5 times 10 to the 6 meters per second, which is just 5 times 10 to the 4 meters per second. Okay? Now we've got that. The mass of the electron is not given here, but you can look that up pretty easily. So let's figure out what delta x is. So it's h, which is 6.626, times 10 to the minus 34. I'm going to write it as kilogram meters squared per second. That's h. I'll put it in parentheses. Over 4 pi. Now, look, we only have one sig fig in this number, 5 times 10 to the 6, so we don't need to use the full value from your calculator. I'll just do 3.1415. That's 5 sig figs. That's way more than we need. 4 pi m, the mass of the electron, 9.109, times 10 to the negative 31 kilograms. And then the uncertainty in the velocity is right there. 5 times 10 to the 4 meters per second. Okay, let's do the dimensional analysis. Kilograms cancel. We have a meter here and 1 meter there. We have a second here and a second there, so we're left with meters. Okay, so that's good. Position, uncertainty in position should be in meters. Okay, okay, we do have some powers of 10. So what is it? It's h over 4 pi m u, delta u. So h is 6.626 divided by 4 divided by pi, 3.1415, divided by 9.109, divided by 5 times 10 to the 4, 5. So it's 0.0116. That's way more sig figs than we'll need, but that's okay. Okay, so what do we have in terms of powers of 10? We have 10 to the negative 34 divided by 10 to the negative 31 divided by 10 to the 4. So let's combine those. 10 to the minus 34, 10 to the minus 31 times 10 to the 4. Negative 31 plus 4 is negative 27. So that's 10 to the negative 34 over 10 to the negative 27. Now, if it's in the denominator, you have a couple different ways to do it. The easiest way is just subtract the denominator exponent. So negative 34 minus a minus 27 is the same as negative 34 plus 27, which is negative 7. So this is times 10 to the negative 7. So there you go, times 10 to the negative 7. Move it into scientific notation. We got to move it 2 places. So we get 1.16 times 10. Now remember, left is positive, right is negative. So we went to the right with this arrow, so this becomes more negative, 10 to the minus 9 meters. Let's round it. 1 times 10 to the minus 9 meters. By the way, that's a nanometer. So what that says is if we measure the velocity of the electron in the hydrogen atom to a precision of 1%, then we have an uncertainty in the position of the electron that's a nanometer. But here's the issue here. We did the calculation. Calculations are important, but the interpretation is even more important. Okay? I know I erased everything, but that's okay. Here's what happens. We have an uncertainty in the position of a nanometer. But the size of the atom, the hydrogen atom, is an angstrom. How big is an angstrom? The diameter of the hydrogen atom. An angstrom is 10 to the minus 10 meters. But our uncertainty in the position is 1 times 10 to the minus 9 meters. 10 to the minus 9 is 10 times the size 10 to the minus 10, right? This is the same as 10 times 10 to the minus 10. In other words, it's 10 times this size right there. So the uncertainty in the position is this big. This is delta x here. 10 times 10 to the minus 10 meters. The uncertainty is 10 times the size of the known size of the atom. Now, we're not going to talk about how you know the size of an atom, but what this tells us is, according to the Heisenberg uncertainty principle, if we want to know the velocity of the electron to a precision of 1%, which is pretty good, 1% is pretty good, there are physics experiments where measurements can be made to precisions of 1 out of a trillion, so much better than 1%. But 1%, if we know it to within 1%, we now know the position to within 10 times the size of the atom, which is essentially saying we don't know where the atom is even. It could be anywhere in this range here. So if you want to know the position of the atom better, you have to give up information about the position. You have to have a larger uncertainty in terms of the velocity of the atom. So if I said, hey, it's going to be known to 10% velocity, right? In other words, imagine that you're walking at 4 miles an hour, and I say, I want to know it to 1%. That would be 4.04, plus or minus 0.04. If I want to know it to 10%, it'd be plus or minus 0.4. If you want to know the position better, you have to know the velocity less. Okay? That's the Heisenberg uncertainty principle, at least one application of it.